All right, so ever since you learnt Pythagoras, you've always just been wondering how could I find the length of a curve? Because in maths, at some stage, things start to get a curve to them, and you want to know the distance or the length of those types of things. So, for example, if you had this red line here, it's got a bit of a curve to it, and you wanted to know the distance between A and B. Well, how could we work that out? If it was like a piece of string and you sort of pulled it out, how long would that string be between A and B? And without further ado, here is the answer. S equals the integral from a to b of the square root of 1 plus dy dx squared dx. So that is how you find the arc length of a curve. And that's sort of the terminology we use. We call it the arc length. So that's what we're going to sort of unpack a little bit more in this sort of short video. So let's see if we can make some sense of it. The first thing that we can say is we can make a triangle. Okay, we can make a triangle between A and B. And you can see that the hypotenuse of this right triangle would actually have a length that's pretty similar to the red line, right? But it's not exact. And what we want to do is make it exact. So what we're going to do is we're going to do a few things. We're going to call this distance here, the distance between this point, A and B, to be delta x, or the change in the x values. And then we call this delta y, the change in the y values. And then just by applying Pythagoras, we get S, which we're going to call, the distance between these 2 points, the linear distance, shall we say. So sort of this line here, the blue line, is the square root of delta x squared plus delta y squared. So we get something like this. Okay, what we want to do before we look at the next complicated thing there is you would agree that that was it would have been a bit inaccurate, right? It would have been an overestimation or an underestimation. What we want to do is make it more accurate. So what we're going to do is we're going to pretend we just zoomed into that position there. We've got x equals a and x equals b. We've sort of zoomed in. And when you zoom in, things tend to look a little bit more linear anyway. We've sort of got the same situation going on here. Again, this is delta y, this is delta x. But if we were able to take delta x to get smaller and smaller, we could sum all of those hypotenuses together, and then we would get a much better approximation of the area. So if I do that, let me show you what I mean. We could put some lines, we could put smaller triangles there. So we can sort of have a smaller line segment here and then sort of break that distance between A and B up a bit more accurately. So now these blue lines are better approximations of the distance of the red lines, right? So we sort of break it up like that. And then essentially what you get is you're going to get a bunch of different, think about it as like you just get a bunch of different triangles, the hypotenuses of which are better approximations of the distance of the red curve between A and B. And then let it pretend, if these were really, really small, it'd be better and better. I think you get the idea. So, we could call this first triangle S sub 1, S sub 2, S sub 3, S sub 4. You sum all them together, and then it'll tell you the length of the red line between A and B. So if we were to put some sort of mathematical notation around that concept, we would say this. We'd say that S equals the limit as delta x approaches 0 of the sum of this thing, the square root of delta x squared plus delta y squared, from A to B. Okay, so you just take really small triangles and add up all the hypotenuses of those triangles. Okay, what we're going to do from here is we're just going to look at this and we're going to say, all right, let's take delta x squared out as a factor. And you'll see why in a moment, but we're taking delta x squared out as a factor. So you'll be left with 1 plus delta y squared over delta x squared. And then the square root of delta x squared is just delta x. So that can sit outside the square root. So you get this, everything else stays the same. And then I've made other videos before, sort of the definition of the integral, but essentially this is the definition of the integral, right? The integral from A to B of the square root of 1 plus dy dx squared dx is this thing, right? And you're probably like, why did you just change the notation? Well, delta y over delta x is kind of like a fraction. And in other videos as well, we've spoken about the fact that we can actually treat the derivative of y with respect to x as a fraction. And so hopefully it's not too much of a leap to say, all right, we can go from this line to our definition of the arc length of a curve, which is this. Okay, so the integral from a to b is the square root of 1 plus the derivative of y with respect to x squared dx. And then from there, your job will be you get given a bunch of problems, different functions, and you have to work out the length between those lines. And this is the information that you'll need. So I think it's pretty cool. It's a very cool way to find out the length between 2 points on a curve. So have fun using that, and good luck with all your studies. See you soon.